the forgotten World War II brick formula that made mud homes blast-resistant. Cities burned, concrete cracked, steel twisted, and yet, in the middle of all that destruction, some mud houses were still standing. Not bunkers, not reinforced fortresses, just walls made from earth. How did homes built from dirt survive explosions that shattered modern buildings? This is the story of a forgotten World War II brick formula. A material so simple it looked primitive, yet behaved in ways that modern blast science is only beginning to fully appreciate. During World War II, bombing campaigns exposed a brutal truth about construction. Concrete is strong under steady load. Steel resists tension. Stone withstands compression. But blast waves are different. An explosion doesn't apply slow pressure. It delivers a violent shock, an instant spike of force. Rigid materials hate that. When the shock wave hits, stress concentrates, cracks form, fragments explode outward. Walls don't just collapse, they become shrapnel. Investigators surveying bombed cities notice something strange. In certain rural regions, particularly in parts of Europe and North Africa, earthen homes were damaged, but not obliterated. Nearby concrete buildings had shattered. The mud houses? Cracked, yes, but standing. Why? Traditional adobe bricks are simple, clay-rich soil, water and straw, shaped and sun-dried. At first glance, that's all these homes appeared to be. But, closer inspection revealed something more complex. The bricks were unusually dense. The fibres inside were thicker and more abundant. Traces of lime and ash appeared in samples. Some even contained animal hair or shredded plant fibres woven through the clay matrix. This wasn't random dirt, it was a composite material. Decades before fibre-reinforced composite became an engineering buzzword. To understand the mystery, you have to understand blast physics. When a bomb detonates, it creates a high-pressure wave travelling faster than sound. When that wave hits a wall, energy transfers almost instantly. Rigid materials reflect most of that energy back. That reflection creates internal stress. The result? Brittle fracture. Concrete performs well under compression, but under sudden dynamic loading, it can fail catastrophically. Mud brick behaves differently. It's less dense, more porous, slightly flexible. Instead of reflecting the entire shock wave, it absorbs part of it. Tiny internal air pockets compress. Micro-cracks form gradually rather than instantly, and when fibres are present, those fibres bridge the cracks, preventing them from spreading too fast. The wall doesn't explode outward, it yields. During the World War II, supply chains collapsed. Cement and steel were scarce in many regions. Engineers and builders had to rely on local materials. So they experimented. Clay soils were blended more carefully. Fibre content was increased intentionally. Lime was added, not enough to turn it into concrete, but enough to stabilise the clay chemically. Wood ash altered internal bonding. The result was something subtle but powerful. A brick that combined compressive strength with controlled flexibility. Under blast pressure, it could deform slightly without disintegrating. Here's the counterintuitive truth. In explosions, harder isn't always better. Ultra-rigid walls, you see, reflect more energy. That reflected energy increases internal stress. Slightly flexible walls, on the other hand, absorb energy. They spread the force over time and space. It's the same reason modern blast-resistant structures use layered composites and shock-absorbing materials. Energy dissipation is, quite simply, survival. Those wartime mud bricks, reinforced with fibres and partially stabilised with lime, did exactly that. They cracked but didn't fragment into lethal debris. And that difference could mean the difference between life and death. After the war, massive reconstruction began. Concrete symbolised progress. Steel meant strength. Glass meant modernity. Mud did not. Industrial cement production scaled rapidly. Governments invested in highways, high-rises and standardised building systems. Earth-based construction was dismissed as outdated, associated with poverty rather than performance. Research into earth and blast behaviour faded into obscurity, not because it failed, but because it didn't fit the industrial narrative. Concrete factories drove economies. Mud bricks did not. And so the knowledge quietly slipped into the background. Today, materials science confirms what those wartime observations hinted at. Fibre reinforcement increases toughness. Controlled porosity improves energy absorption. Lime stabilisation enhances compressive strength while reducing brittleness. Modern engineers design fibre-reinforced concrete using the same principle. Prevent catastrophic cracking by distributing stress through internal fibres. The ancient mud brick, modified during wartime necessity, was operating on the same physics. Controlled cracking, energy absorption, reduced fragmentation. In fact, some contemporary tests on stabilised adobe show impressive structural resilience when properly engineered. It isn't just sustainable, it's smart. Were these blast-resistant mud homes the result of deliberate military research? Or simply generations of traditional knowledge accidentally optimised by necessity? The answer may be both. Fibre reinforcement in clay dates back thousands of years. Ancient builders understood that straw prevented cracking during drying. But wartime adjustments, higher lime ratios, tighter compaction, careful curing suggest experimentation under pressure. When survival is on the line, innovation accelerates, even if it never makes headlines. There's another overlooked factor. Lower density materials create less deadly debris when they fail. Concrete fragments can become high-speed projectiles. Earthen materials tend to crumble rather than explode outward. In bombed regions, this mattered. A partially damaged mud wall might still provide shelter. A shattered concrete wall could turn lethal. Survival isn't just about standing tall. It's about failing safely. As climate change, resource scarcity and conflict reshape the world, architects are once again exploring earth-based construction. Compressed earth blocks, rammed earth walls, fibre-stabilised clay composites, not as primitive alternatives, but as advanced sustainable systems. With proper engineering, these materials can be fire-resistant, thermally efficient and structurally resilient. The lesson from WWII isn't that mud is stronger than concrete. It's that intelligent material design matters more than prestige. Flexibility can outperform rigidity. Adaptability can outperform brute strength. In a world obsessed with harder, taller, stronger, we may have overlooked something simple. Walls made from earth, reinforced with fibres, stabilised with lime, once withstood the shock of war better than expected. not because they were indestructible, but because they absorbed energy instead of fighting it. The forgotten WWII brick formula wasn't magic, it was physics. And perhaps the next breakthrough in resilient housing isn't hidden in futuristic alloys or secret bunkers, but in the dirt beneath our feet,